Leah here from LeahForSci.com, and in this video, we're going to look at some practice problems drawing Lewis structure, identifying molecular shape, hybridization, and polarity for molecules. As a reminder, for Lewis structure, we're looking to draw every atom, electron, and bond on the molecule. That will give us the molecular shape, which is the three-dimensional structure. The hybridization tells us what orbitals were fused to create the bonding on that central atom, for example, sp3, sp2, or sp. And the polarity shows us if we have a difference in electronegativity so that the overall molecule has partial negative and partial positive charge, or if it's completely neutral. If you're not comfortable with these concepts, go back to the tutorial videos on my website where I walk you through all of this. You can find them linked below, or go to leahforsci.com/intro-orgo and leahforsci.com/orgo-basics. Ready to jump in? Let's start with a warm-up, CH3Cl. The first thing we want to do for the Lewis structure is identify the central atom, typically a carbon. We know that carbon can have up to 4 groups attached, and if we have H3 and Cl, these are the 4 groups, so I just place them around the carbon atom. This gives me 3 hydrogen and 1 chlorine. Once we have the atoms, connect them all with a single bond, and then let's see if we're missing any electrons. How many valence electrons do we expect to have on this molecule? Well, carbon should have a total of 4. Hydrogen should have 1 each, gives me 1 times 3 is 3. Chlorine should have 7, for a total of 14 electrons. You can find these numbers on the periodic table, but in organic chemistry, you're going to come across 10 atoms so often that it's worth memorizing, and I show you how to memorize them specifically in the periodic table video link below. Let's see what we have for electrons. 1, 2, 3, 4 around carbon. 1, 2, 3 connecting the hydrogen, that's 7. An 8th one, carbon to chlorine. 9, 10, 11, 12, 13, 14. All of the atoms have a verified complete octet. 8 for carbon, 8 for chlorine, and hydrogen is an exception where it only needs 2. We have our Lewis structure. What can we tell about the shape of this molecule? Well, it kind of looks like a flat cross, but it isn't because the Lewis structure is 2-dimensional and this molecule is 3-dimensional. Anytime you have a central atom with 4 groups attached to it, you should recognize that the hybridization for this is sp3, having 4 groups, which means that the molecule is a tetrahedron or tetrahedral. What about polarity? Carbon and hydrogen have a nonpolar bond. Carbon and chlorine have enough of a difference in electronegativity where the electronegative chlorine is pulling electrons away from carbon, making carbon partially positive, giving me a dipole in the direction of chlorine. Let's try another problem looking at HCN. For the Lewis structure, let's start with the central atom, which is a carbon, and place the other groups around it. Now we don't have 4 groups to put around carbon, so we'll take what we have, put hydrogen on one side, nitrogen on the other, and connect each one with a single bond. How do we know if we're done? We don't until we account for all of the electrons. Hydrogen should have just 1 valence, carbon has 4, nitrogen has 5, for a total of 10. Right now I have 1, 2, 3, 4. That's no good. The question then is what to do from here. This is where students get stuck. How do I figure out the number of lone pairs? Or maybe pi bonds? The method that I teach in my videos linked below is to first give every atom a complete octet and then compare it to the number of electrons that you should have. If you have too many electrons, we're going to cut out duplicates on neighboring atoms and put pi bonds between them. I know this may sound confusing, so if you haven't seen that video, make sure you watch that first. But if you're comfortable with it, let's take a look. To complete carbon's octet, we want 8. So far, I have 4, 5, 6, 7, 8. To complete nitrogen's octet, we only have 2, so we have to add 3, 4, 5, 6, 7, 8. But here's the problem. If we count up our electrons, we have 2, 4, 6, 8, 10, 12, 14. We have 14. We should have 10. That means we have 4 extra, and we have to get rid of it. How do we get rid of 4 extra? We take a pair. That's 4 gone. Replace it with a pi bond. We replaced 4 with 2. We have 2 extra. So we'll do the same thing again over here. Got rid of 4, replaced it with 2, and we have no extras. Let's verify just to make sure we did it correctly. Hydrogen has a single bond to carbon. We gave carbon a triple bond to nitrogen, and nitrogen has 1 lone pair on the right side. Let's count our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of electrons are correct. Does everything have a full octet? Nitrogen has 8. Carbon has 8. Hydrogen is an exception to the rule. We have our structure. To find the shape of this molecule, we look at that central carbon, and it only has 2 groups coming out of it, one to the right, one to the left, making it a straight line, or linear, telling us that the hybridization of that central atom is an sp hybrid. If you're curious, nitrogen is also an sp hybrid because it's got 1 and 2 groups coming out of it. We won't find polarity between carbon and hydrogen, but nitrogen is slightly more electronegative than carbon, and that means it's pulling on the electronegativity, creating a dipole in the direction from carbon to nitrogen. For the next molecule, let's look at SO2, which seems very innocent, but can get very confusing. Because we don't have a carbon, do we choose sulfur or oxygen for the central atom? I like to start with a less electronegative atom and put the more electronegative ones around it. So if we have a sulfur, we can put an oxygen on either side and connect them with a single bond. What else do we need for this molecule? Well, how many valence electrons do we have? On the periodic table, sulfur is under oxygen, so they have the same number of valence electrons, and that means if each is 6 times 3, 1 sulfur, 2 oxygen, we expect a total of 18 electrons. And so far, all I have is 4. Let's start by completing all their octets and comparing what we have. A quick count tells us that we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 20 electrons. We only want 18. That means we have 2 extra that we're going to get rid of by creating a pi bond. We get rid of a lone pair each on sulfur and oxygen and put a pi bond between them. To redraw it cleanly, we see an oxygen with 3 lone pairs bound to a sulfur with 1 lone pair, double bound to an oxygen with 2 lone pairs. To find the shape of this molecule, we can't simply say it's linear with sulfur having 1 group to the right and 1 group to the left, because that lone pair also counts as a group impacting the shape of the molecule. So to draw it more correctly, we would have the lone pair on sulfur taking up a lot of space, forcing the oxygen to shift upward a little bit, forcing that other oxygen to also shift up a little bit, giving me a molecular shape of bent. Now, if you were thinking, wait a minute, if I have 3 groups, it should be trigonal planar, that would be correct if there was an atom bound here. Having 3 bound groups gives you trigonal planar. Having only 2 bound groups, where the third one is a lone pair, gives you a bent molecule. And the hybridization for the central atom, just like something that's trigonal planar, is going to be sp2 hybridized. If you've already studied resonance and formal charge, tutorials for both are linked below, then you'll recognize that there's a formal charge of -1 on the oxygen and a formal charge of +1 on sulfur, which would make you realize that we have an unconventional resonance structure where that central sulfur atom can have 2 oxygens, both double bound, and still have a lone pair. If you're thinking, wait a minute, Leah, doesn't this violate the octet rule? Sulfur now has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You would be right to think so, except that sulfur is an exception to the octet rule, and it can have more than a total of 8 electrons in its outermost shell. What about polarity? Given that sulfur and oxygen are somewhat close in electronegativity, we wouldn't expect much polarity, but sulfur is still slightly more positive, oxygen is slightly more negative, And in this situation, they appear to cancel out, which is why it's important to recognize that we have a bent structure, where even though the oxygens are each pulling electronegativity away from sulfur, both of them are pulling in the slightly upward direction, which means that the net dipole on this molecule will be canceled out from the right and left, but will go slightly upward away from sulfur towards the oxygen. Are you ready to try even more practice? First, make sure to give this video a thumbs up and subscribe to my channel so you don't miss out on any new videos. And then, if you're looking for even more practice, check out my General Chemistry Basics for Organic Chemistry Practice quiz, which you can find on my website, along with the introductory videos that teach you these concepts by visiting my website, leiaforsci.com/introorgo. The link again, leiaforsci.com/introorgo.